Example 1. More friction examples. Consider the bench below, which is being pulled by student number 1. You know what? I'm going to make student number 1 Acacia. I'll put an A there. And specifically, let's make it those benches in the gym, at the back of the gym, the ones that you sometimes have to slide around. You've slid those around at least. Okay. And you're pushing it at a constant speed. That's going to be important. That's a really useful phrase in this unit. Student number 2, Ella, pushes down, sits down on the bench while you're pushing it. You've all seen that happen at least once. A kid's pushing the bench and one of their friends comes along. I'm going to sit on it while you're pushing it. Now push. Okay. If Acacia maintains the same force as before, what happens to A, the weight, B, the normal force, C, friction, and D, motion of the bench? You know what? I think this would be a good job for a good free body diagram. Although, Eric, they did a free body diagram for the first situation. There's the applied force, gravity, normal force, and friction. Okay. Let's go. Here's the second situation. Now Ella's sitting on the bench. Well, what are the forces acting on the bench? Get the obvious one. Bigger, smaller, or the same size as the bench originally? Has the mass of the bench changed? Has gravity, G, changed from 9.8 to something else? So I ask you again, bigger, smaller, or the same size as the one originally? So draw an arrow the same size as the mg originally. I'll call it mg. And that's going to answer, Clody, part A. Part A says, what happens to the weight? Remember, another word for weight is the force of gravity. Stayed the same. Let's go back to our free body diagram. Is this sinking into the ground like quicksand? Is it flying to you like Superman? So what force must be pushing up? What force must be pushing up? Normal force, bigger, smaller, or the same size as mg. Certainly in the first situation, they were the same size. What about here? Why must it be bigger than gravity? Because now it's having to cancel out mg of the bench. And what else? Ella! F Ella. Yeah, F. Oh, no, that came out wrong. The force of Ella, right? So I'm going to exaggerate it, but I'm going to say, you know what? The normal force is now bigger. The mass of the bench didn't increase, Sana. What did increase? How hard the ground has to push up through the feet of the bench. And so we can answer that for part B. What happened to the normal force? The normal force increased. I'll write that as Fn and then an up arrow. Ella, friction is what times what? Good. What happened to the normal force in part B? So what happens to the force of friction in part C? Has to. So you know what? I'm going to write friction increased. And in my free body diagram, how do I know friction is longer? Because originally Acacia was pushing at a constant speed. Friction was exactly the same size as F Acacia. Now, it's bigger. Looking at this free body diagram, which way is this bench moving? Still to the right, but which way must it be accelerating? So how will this bench, it says describe the motion of the bench. How will this bench behave? Slow down and come to a stop. It's going to slow down and come to a stop. Then Acacia's going to flip the bench over. Ella's going to land on the ground, start crying, and then we can start moving the bench over again. Right? Right. It says explain your answer using principles of physics. I think we kind of did with the free body diagram walking through. I would live with that as a good explanation, I think. Okay. If we weren't in a COVID year and I had more time, I would talk about the fact that technically there's two different mu's, two different coefficients of friction. One when the object is at rest, and 1 once it starts moving. And Eric, it's kind of nerdily cool, but I'm going to skip that. You can cross that out. And I'm going to skip that. You can cross that out. And in fact, you can go to the page that says, to keep the math nice. It says, to keep the math nice, we will treat both types of friction as the same. We're going to pretend there's one type of friction. So what does that mean? Ella, friction is what times what? Where another word for mu is the coefficient of friction, not the force of friction itself. And the normal force we get from our free body diagram, because I've never given you an equation for normal force. There isn't one. Do a free body diagram and figure out how big it needs to be to keep the object from sinking into the ground like quicksand. By the way, friction is a bit of a weird force, especially when an object is at rest. When an object is at rest, friction is only as big as it needs to be. Sorry for those of you at home on YouTube. I'm going to be doing a demo in class, but you're not going to get it. Example 4 says, find the maximum force of friction between the mass and the ground for the following objects. You can cross that last thing out. That would have been if I was telling you that there was 2 types of friction, and I'm not this year. Okay, let's zoom in on the first picture. What does it want us to find? The maximum what? Force of friction. This is a job for a free body diagram. What are the forces acting on this 8 kilogram mass, Zana? Get the obvious one. Yep. What else? Now, you're going to start to notice, because we've done a bunch of free body diagrams, I'm going to give you fewer and fewer hints. So I used to do along, is it sinking into the ground? Is it flying? And now more and more, I'm just going to start to say, what else? What else? And see if you can develop that own pattern in your brain. So what else? Bigger, smaller, or the same size as mg? Good. By the way, look at B and C. I don't think the normal force is going to be the same size as mg. How can I tell at a glance that the normal force isn't the same size? Because there's extra vertical forces in those pictures. That's mucking it up. Okay. So, friction is what times what? Zana? What's mu? I don't know. What's mu with you? What's mu? 0.35 from the picture. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? In fact, if I want to generalize what you've really, without realizing it, you've said something profound. You said, look, if it's not sinking into the ground like quicksand, and it's not flying here like Superman, everything down has to equal everything. You okay with that? That's Newton's first. Okay. So we're going to say for this specific example, it's mu mg. And let's crunch the numbers then. Friction is going to be 0.35 times 8 times 9.8, which is what? It's going to be in the 20s somewhere, I think. 27. Give me all the sig figs. 27.44. Anybody else? I mean, I don't trust L. Yeah? Okay. Units, it's a force. Units, it's a force. Newtons. Okay. So, Zana, what's the biggest friction can be? Read me that number. What if I pull with 20 newtons, though? How big will friction be in the opposite direction? Not 27.44. How big? 20. How do I know? It's not accelerating. What do I pull with 25? It'll be 25. If I pull with 27.43, I would be able to tell through the rope, this is almost ready to go. All of you maybe have pushed or pulled on something and could, yeah, it's almost ready to start to slide. If I pull with 27.45, it'll accelerate. Once it's moving, if I pull with 27.44, it'll keep going at a constant speed. If I pull harder, it'll accelerate. Is that okay? Is that raining outside? Probably hail. Okay, it's called a distraction. Deal with it. You know what? Cohen was looking all around, so let's see if Cohen can deal with the distraction. Cohen, let's do B together. It wants us to find the force of friction. You know what this is a good job for? What are the forces acting on it? Get the obvious one. Good. What else? Bigger, smaller, or the same size as mg? Why? You're right. Why bigger? Because now gravity is having to cancel out mg, and it's having to cancel out that 55. I'm going to exaggerate it so it catches my eye. What does this question want me to find? Friction is what times what? I don't know the normal force. Oh. And I can't easily say, oh, but look. You know what? Are we sinking into the ground like quicksand? Are we flying into the air like Superman? Then what that really means is everything down equals everything. Turn that into equation. What's everything down? Your hint is there's two things. Don't overcomplicate it. Instead, Fn is down? Okay, and you said mg and 55? What does the word and mean in an equation mathematically? Look, everything down has to equal what's everything up? And the arrow pointing up. Okay, so you ready? Cohen friction is what times what? Mu times the? I don't know. Wait a minute. Apparently the normal force can be replaced with what? It's not what we wrote. What can the normal force be replaced with? Yeah, not mg. Don't you dare say that. Mg plus 55. Look up. How will I do that? It's going to be this. Mu bracket mg plus 55. Because if the mu is multiplying the entire normal force, it better multiply the entire normal force. Now I can start to plug in some numbers. What's mu? I don't know. What's mu with you? 0.35. And then in brackets, it's going to be 8 times 9.8 plus 55. I know the answer is going to be bigger than 27.44, but otherwise I'm not sure. What do you get? Give it to me give me all the sig figs. 46.69? Newtons. If I pull with 5 newtons, how big will friction be? 5. If I pull with 46 newtons, 46. But if I pull with 50 newtons, 46.69 in the opposite direction, who's winning? The 50. Who's losing? The 46.69 winner minus loser equals MA. Ooh. Okay. Huh. Scott, this is a job for a free body diagram. What are the forces acting on this, Scott? Get the obvious one. Yes. Well done. What else? Bigger, smaller, or the same size as mg? Yes. Why? Because someone's lifting up with 55 newtons, so the ground only has to get what's left. I'll exaggerate it so it catches my eye. Good, Scott. Well done. Okay. Well, friction is what times what? I don't know the normal force. And this is not like A, where I can easily say, oh, it's the same size as mg. I better write out an equation. Are we sinking into the ground? No. Are we flying to the, then everything down has to equal everything? Turn that into an equation, please. I'll give you a hint. Here's everything down. Has to equal. I'm going to write Fn plus 55, but I would give you full props for 55 plus Fn. Why did I write it that way? Because I want to get the Fn by itself, and it's a tiny bit easier to see how to do that. How would I get the Fn by itself, Scott? Yes. Good. apparently the normal force is going to be mg take away 55. Okay, I can do this. It's going to be mu bracket mg take away 55. You know what? If you have a good calculator, if you did B, I think it's the same equation, but instead of a plus sign, you've got a minus sign. You can probably just backspace, bring back your previous calculation, change the plus to a minus, and hit equals. Or you can retype it from scratch. And once you're done, Scott, let me know what you get. I think you're going to get something a little under 10, I think. But don't quote me on that. I'm doing some really rough guesstimations. 8 point something or 9 point something, I think. What'd you get? Okay. So, what's mu? You do. Look at the picture. What's mu? 3.5? What's mu? Okay, so on your calculator, 0.35 times, open a bracket. What's m? Type 8 times 9.8 minus 55. Close off the bracket. And with a nerdy thrill of pride, tell me what the answer is. 8.19, yes? Good. See where you might have zigged the first time? Good. So, to get A accelerating to the right, you would need to pull with more than how many newtons? 27.44. To get B accelerating to the right, you would need to pull with more than how many newtons? And to get C accelerating, 8.19 newtons. And I've kind of done that to try to explain why, if you're at the age where over the next few years, you and your friends will all be moving out and you'll be helping each other move furniture. And so you will come to a point when something is so heavy, you can't actually lift it, but you also don't want to scuff the floor, so you'll lift up while sliding it to reduce friction. That's why. That's why the 8.19 is the smallest. You can reduce the normal force even if you can't get rid of it. Yeah. Quick like a bunny. Example 5 says this. For each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, and find the acceleration. You know what? I'm going to kind of do this simultaneously. Oh, that didn't work. There. Draw a little line down the middle of your page. Claudia, what does A want me to find? Read me the whole thing. What does it say? Vertical force equation? I'm not going to do that. I can just, by them asking me that, how should I start this off? Free body diagram. You and me, we're going to do the free body diagram for both of these. Let's start on the left. Chloe, what are the forces on this 10 kilogram mass? Get the obvious one. So, mg. What else? Bigger, smaller, or the same size as mg? Yep. Good. Then I noticed that 20, that's the mystery force coming from off the page. What name did we give to that the other day? A mystery force coming from off the page. Do you remember? This is what we called the applied force. It was just a generic, something's applying a force. Okay? So I'm going to put an arrow, and next to the 20, I'm going to go equal F applied. Do they want us to include friction? How do you know they want me to include friction? They gave me a coefficient of friction. So, assuming F applied is causing us to slide to the right, which way will friction be pointing? Yep. Bigger, smaller, or the same size as F? I think smaller. I'm going to guess smaller. I'll know I've guessed wrong if I get a negative acceleration. But for now, I'm going to say good. Let's do the right-hand diagram. What are the forces acting on? Get the obvious one. What else? Go systematically. Go in the same order. Normal for bigger, smaller, or the same size as mg here. Give you a hint. Not the same size because I see an extra vertical force. So bigger or smaller? Which way is the extra vertical force pushing? So is that adding to gravity or subtracting from gravity? So is the normal force going to have to push harder or less hard? So is the normal force bigger or smaller than mg? Yeah. See how we put that together? Awesome. And then, Claudia, we still have F applied of 20. What else? I think we're still including friction. I think it's still smaller. It's bigger than before, but I'll gamble that it's smaller. We'll see. Cool. Excellent. Okay. Mallory, A says write a vertical force equation. Yeah. Okay. On the left-hand side, are we sinking to the... You know what? The vertical force equation for an object sitting on the surface, if it's not sinking into the ground like quicksand, and it's not flying through like Superman, the vertical force equation is everything down equals everything. So can you turn that into an equation for me? Yep. Yes. What about on the right-hand side? A little tougher. But it's still going to be everything down equals everything up. You've missed a down. Everything down. What other arrows point? The normal force is pointing down? I disagree. Oh, that 15, which I hardly know. Yeah. So by the way, a habit you might want to do when you're, just to make sure you don't forget, you might even want to color on that 15 with ink or something so it stands out to your mind so that your brain has said, I saw it, I cataloged it. Everything down, mg plus 15 has to equal everything up. Okay. Jada, what is C, oh, sorry. Yeah, sorry. What does B want me to do, Jada? That's easy. Friction is what times what? Mu times the normal force. And over here, friction is what times what? Still mu times the normal force. Back to the left. I don't know the normal... Wait a minute. Yes, I do. Mallory, what's the normal force the same as? Okay. So I can say mu mg. Let's plug in numbers. That's going to be, Jada, what's mu? I don't know. What's mu with you, Mr. Duke? What's mu? 0.12. M, 10. G, 9.8. Which is what? Oh, I can do this in my head. It's going to be 98 times 12. It's going to be 9.8 plus 1.96. It's going to be 10.8. 11.76, I think. Double check me, Jada. 11.76? Four sig figs in my head. Okay. It's a force, newtons. On the right-hand side, friction is mu times the normal force. I don't know. Wait a minute. Yes, I do. Now, what's the normal force the same as, apparently? So are you telling me that I can go mu bracket mg plus 15? That's friction? Oh. Well, let's plug in numbers. It's going to be not 0.35, Mr. Dewick, 0.12. 10 times 9.8 plus 15. Do that one in your head, Mr. Dewick? Well, maybe. 10 times 9.8 is 98 plus 15. That's going to be 108. It's going to be 113. 113 times 0.12. It's going to be 11.3 plus 2.26. It's going to be 13.3, 13.5, 13.56? Yes? Newtons. Fahim, what does C want me to do? What that's really saying is winner minus loser equals MA. In the first situation, who's winning? Which way is that box probably accelerating? To the? So who's winning? To the right. Which force is pointing to the right? Who's losing? Equals? Yep. On the right-hand side, Fahim, the second diagram, who's winning? Who's losing? Equals? Mr. Dewick, it's the same equation for both. Doesn't that mean I'm going to get the same answer for both? No. Because it's different frictions in both. Sophie, what does D want me to find? Oh. How would I get the A by itself? Scott's theorem. So you're telling me A is going to be F applied minus friction divided by M. What about the equation on the right-hand side? Really? All right, Sophie, let's stick in our numbers. I think we can do this. A is going to be F applied was 20 minus friction was 11.76 divided by 10. Oh, I can do that in my head. 20 take away 11 is 9. Take away 0.6 is 8.7. Sorry, take away 0.7, 8.3. 8.2, 0.824? Or not? 0.824? Anybody else? Yeah. Acceleration, so meters per second squared. Cohen seemed pretty impressed when I did the last math in my head, but Cohen, it's actually a bit more of a parlor trick than you realize, because in this question, most of the time, I'm dividing by 10. So Cohen, you and I are going to do this in our head together. No calculator. You ready? This is how my brain does it. 20 take away 13. Take away 0.5, 6.5. Take away the 0, 6.44. Divide by 10. The decimal just moves over one spot. So instead of 6.44, 0.644. That's how I do it. Meters per second squared. By the way, if you haven't figured it out, if you are doing math in your head, you actually do math in your head backwards from the way that you write the math doing it by hand. You do math in your head from left to right. You do math by hand using like the borrowing and carry the one and all, from right, working way to the left. Ah! Here we go. Turn the page. Sorry, YouTube. Class was looking a little dozy. For what it's worth, YouTube, a good dozen of them jumped that time. After that, okay. Cause and effect? I hope not. You do not need to memorize this. This is purely for nerd trivia. I wanted to give you some common coefficients of friction. So wood on wood, fairly slippery. Wood will, if it's sanded, wood will slide across wood okay. It's not great, but it's okay. Steel on steel, not good. Wait a minute, Mr. Dewick. We make our machines out of steel parts, and they're all rubbing against each other. Yeah, how do we reduce friction? What do? Looking for a word that starts with the letter L. We lubricate. That drops to about 0.1. And now it's pretty slippery. Add oil. Rubber on dry asphalt. This one varies an awful lot from 0.4 up to about 0.8. You may have noticed On a hot summer day, like a really hot day, like when it's 36 degrees, is pavement stickier or slipperier? Yeah, pavement, the mu is affected by temperature and things, so this is a rough guide, but here's what I do want you to notice. When it rains, the coefficient of friction drops by around what? A factor of about what? A half. You got about half as good traction. You know what that means? It means it's going to take you twice as long to stop. Twice as far to stop than you're used to. So, slow down. I'm a good driver. Don't argue with the physics. When it's raining, slow down. Rubber on ice, really slippery. That's why walking on ice with sneakers is really, really tough. Steel on ice, a little bit better. Can we have a coefficient of friction bigger than 1? Yes. I have to be careful. You can think of it as glue, but glue is not a friction phenomena. It's often a molecular bonding phenomena. But a good way to imagine that would be to say it would feel like glue. A dragster has a coefficient of friction on its tires of 2.8, very high. Shouldn't a tire with so much friction slow the dragster down? Explain, using principles of physics, why you would want a high coefficient of friction on a dragster tire. And you do. You know what this might be a good job for? This is the free body diagram that I was at a conference and the physics teacher did incorrectly. So let's see if we're better than that physics teacher. How should we start? We would start with friction? I have never started. How should we start? How have I started every single... It should be obvious. Should be obvious by now. What? You said mg? I'm sorry. I thought you said friction. I was like, what? Okay. What else? Yeah, let's go systematic. It's not sinking to the ground. Okay, so we have normal force. Now we need to think a little bit deeper. Let's decide, just so that our pictures all look the same, that it's accelerating to the right. Which way is it accelerating? To the? Which way must there be an arrow pointing then? Has to be to the right, right? Newton's first. Okay. What force is that? I'm going to show you what my physics teacher colleague wrote. Don't write this down. And tell me why this must be wrong. They did this. Is it the engine that makes the car go forwards? So, I had to gently explain to them what hopefully you've realized. What force is that? Emilio? Friction. It's why a dragster, if you put it on ice and it stepped on the gas, nothing would happen. What force is making it accelerate? Now, we're ignoring air resistance. You can make an argument, don't write this down, that there should be some air resistance. Although, are dragsters pretty aerodynamic? Yeah. So it would be pretty minimal. Okay? That's the diagram. By the way, I like this free body diagram. I like this free body diagram. I like this and I'm not saying that I like this question. Here's what I mean. That's the same free body diagram as when you walk. Friction is what's pushing you forwards. That's the same free body diagram as when you ride on a bike. Friction is what's pushing the bike forwards. That free body diagram there shows up all over the place. Most of the time, when an object is touching the ground and it's speeding up, friction is what's making it speed up. The only exception would be if it had a rocket engine strapped to it. Then it would be F thrust. Fair enough. Okay. How can I make friction bigger? Well, friction is what times what? So increased mu, that's why big mu. Oh, how many of you ever watched a drag race either live or on TV? What do they do right before the start every time? They do something else. They don't just rev the engine. Yeah. They do a burnout. Smoke show. Is that to impress the crowd? No. Be obvious. What's stickier, melted rubber or hard rubber? They're increasing mu again. Now, that comes at the expense of wrecking the tires. They got sponsors. Dragster tires are crazy expensive, but you're not using the tire for more than 1 or 2 races before you're replacing it anyways. They got good sponsors. That's why drag racing is so expensive. But yeah, they know their physics. You do a smoke show, you're melting the rubber. Of course, you've increased mu. Is that okay? Have I convinced you with that free body diagram? Okay. That free body diagram in yesterday's lesson can be used to answer some of the questions I told you to put a star next to. Not all of them, but some of them. We're going to finish with example 7. You've been very patient. A force of 120 newtons is needed to push a box along a level road at a steady speed. Eric, of course, I would underline steady speed. That tells me an awful lot. If the force of gravity on the box is 250 newtons, Aiden, what does A want me to find? Force of friction. Don't write this down. Look up. My first thought was to go, well, friction is mu times the normal force. Why doesn't that help me at all? What's mu? I don't know what's mu. I don't know what's mu with you. Yeah, no mu. Okay, but my first thought would have been to try that up in my brain. I would have said, well, let's try. Oh, that doesn't work. Okay. Now you can write down part A. Suggestion, Aiden. You're smarter than you look. What do you got? Make that a compliment. What else might we try? What's in our toolbox? What might this be a good job for? Whew, wow. Thought you would have come up with that on your own. Okay. There's the box. What are the forces acting on it? Get the obvious one. By the way, this one's a little weird. I know gravity. How big exactly as a number? They didn't tell me the mass, but they told me the weight. If I need the mass, I'll divide that by 9.8, but maybe I don't need it. What else? Bigger, smaller, or the same size as mg? The good news is one of those 3 answers is correct. You know what? Hang on. Let's just pause for a second here. Aiden, oh clever young lad, I agree with you, normal force. Bigger, smaller, or the same size as mg? How can you tell? You're correct. Level road, next year we'll ask, what if you're on a hill, but for now, level road, no extra vertical forces. I totally agree. Which means if I need the normal force, it'll be 250. All right, what else? Read the question. Read the question. F applied. Oh, did they give me an F applied? Ah, good, good. Good. I'm so glad you spotted that. What else? Which way? Bigger, smaller, or the same size as F applied? What did I underline? So, what? What? Why? Newton's first. I like this question. I'm not saying I like this question, I like this question, I like this question. I'm saying the reason I like this question, it starts out looking so tough. But, Aiden, what do they want us to find? How big does friction have to be exactly as a number? Has to be. No actual calculations required. It comes out of Newton's laws and the free body diagram. I love questions that are so easy that they're tough. They look really, really nasty, and then partway through it becomes kind of a, oh, nice. I have a soft spot for those. You okay with that? Let's redeem ourselves. What does B want me to find? What symbol have we used for the coefficient of friction? You know what? Friction is mu times the normal force. Yes? Get the mu by itself. Yes. Mu is going to be friction divided by the normal force. As a number, how big is friction exactly? That's from part A. I don't know that or do I? How big exactly? Yeah. What's mu? I don't know. What's mu with you? What's mu? I can do that in my head. 0.48, yes? Yeah. Units. And you can see, because it would be newtons divided by newtons, the newtons would cancel. Nothing left behind. Okay? We're going to pause here, and thank you for your patience.